the density function is mathematically it is defined as a derivative of the distribution function. Density function is a derivative of distribution, and in a continuous form, so we can define the density function properties as its value fx of x value is always greater than or equals to 0. This is a positive value because since distribution capital Fx of x is a probability and the derivative of this function is density, that is small f fx of x is the density probability density function. Remember, these two, distribution and density functions, are best descriptions of the random variable. Various properties of the random variable can be understood thoroughly by these two functions. These two are known as the basic functions, distribution and density functions of the random variable. And second one, it is nothing but the sum of all the probabilities. In discrete case, sum of all the probabilities must be equals to 1 for a given random variable. So this is the condition, sigma I equals to 1 to n, probability of xi is equals to 1. In a given random variable, sum of probabilities of all the elements is equals to 1. Alternatively, in continuous form, this is represented in terms of density function as integral minus infinity to infinity fx of x dx. That means this represents the area under the density curve. Integral represents the area under the density curve is equals to 1. In discrete case, the equivalent is sum of all the probabilities must be equals to 1. And third property gives the relation between distribution function and density. Already we have seen density is the derivative of distribution. So alternatively, distribution can be written as the integral of the density function. And fourth property is probability of an event. The similar property we have seen in the distribution function also. Probability of the event x less than or equals to x2. That means random variable value lies between two integers x1 and x2. In terms of distribution, it is the difference. Similarly, the same event in terms of density, since it represents a continuous function, integral x1 to x2 fx of x dx. So the probability of this event in two ways we can express, in terms of either in terms of distribution function or in terms of the density function. So we will see one example for distribution and density functions, how to draw the distribution and density functions and how to find out, how to express mathematical expression for the distribution and density functions. This is the problem. A random variable values are given as -3, -2, -1, 0, 1, 2. 6 values are given and the corresponding probabilities are also given like that. Here there is an unknown variable k. The problem is find the value of k, find distribution, density and draw the plots. So this is the actual problem. Distribution is given, that means values, x values are given, corresponding probabilities are also given. As well, we know that the sum of all the probabilities must be equals to 1. This is the basic rule in probability. That means all the possible values of the random variable and the corresponding probabilities. If you take the corresponding probabilities, sum of all the probabilities must be equals to 1. So apply this rule and find out the sum, find the k value. We will get the k value as 0.25. Now change the probability values by substituting k equals to 0.25 as, so these are the values we got, 0.2, 0.125, 0.25, 0.1, 0.075 and 0.25. So after finding out the k values, it results the probability values like this. And we know the distribution, random variable values, here I am writing -3, -2, -1, 0, 1 and 2. So these are the possible random variable values and these are the corresponding probabilities. So fx of -3, what is fx of -3? Fx of -3 is nothing but probability of x less than or equals to -3. So how many elements are there satisfying in this relation, x less than or equals to -3? Only one element, that is -3, and the corresponding probability is 0.2. So fx of -3 is 0.2. Similarly, I will take randomly one value, fx of 1. Fx of 1, that means probability of, this is probability of x less than or equals to 1. So totally how many elements satisfying this relation, x less than or equals to 1? -3, -2, -1, 0 and 1. Totally there are 5 elements. So fx of 1 is sum of all the corresponding probabilities, probability of -3, probability of -2, -1, 0 and 1, that is 0.75. Similarly, we can find out all the values. See fx of 2, what is fx of 2? Fx of 2 is sum of all possible values in the random variable. So obviously its value 1 is 1 and even thereafter if you take any value after 2, fx of 3, fx of 4 up to infinity, its value is 1 only. That means maximum value of the distribution function, as already we have seen in the properties of the distribution, its value is 1. And see, this is the mathematical expression. So mathematical expression consists of the probability of each element into u of x minus that element value. See, first element is minus 3, corresponding value, probability value is 0.2. So 0.2 into u of x minus of minus 3. So x plus 3, 0.125, that is second probability into u of x plus 2. Yes, this is a mathematical expression for the distribution function. Now let us see how to draw this distribution function. So to draw the distribution function, take the horizontal axis. Horizontal axis consists of random variable values. Vertical axis is the distribution function. So first draw what are the possible values: minus 3, minus 2, minus 1, 0, 1 and 2. So these are the possible values. Now let us see what is the first value, that is probability at minus 3. Probability at minus 3 is 0.2. So write a step with a magnitude of 0.2 here. And next value is occurs at minus 2. To that point, the same value continues for the distribution function, that is 0.2 only. Only the probability value changed at x equals to minus 2, and at x equals to minus 2, the probability value is 0.125. So again, one more step occurs at 0.125 with a magnitude of 0.125 at minus 2. Similarly, the steps will occur only at where the random variable is having the values, and finally at x equals to 2, its value, this is the step and the whole magnitude. If you observe this distribution function, so you have to remember 2 points. Step value, this particular step occurs at the random variable value, where the random variable consists of, here random variable values are minus 3, minus 2, minus 1, 0, 1 and 2. So step occurs at minus 3, and magnitude of this step, like this, magnitude of the step at minus 1 is equals to the probability of that particular element. That is, at minus 1, the probability of minus 1 is 0.25. So the step value at minus 1 is equals to 0.25. And these values, let us say, here I have written 0.2, 0.325, these are the distribution function values. In the expression of distribution function, we can observe 0.2, this is 0.2, next 0.2 plus 0.125, that is 0.325, then 0.325 plus 0.25, 0.575, like this. These are the distribution function values. So it is a staircase form, step form. So that's why these unit step functions are having some significance in the representation of distribution function. Similarly, density. For the same random variable values, density function is the derivative of distribution function. So derivative of step. What is the derivative of step? As we know, derivative of the unit step is nothing but the impulse function. Impulse function means which is having the magnitude is equals to this one. Suppose if you let us write 0.2 into del of x minus 3, x minus of minus, that is plus 3. This 0.2 is the magnitude of this impulse, and del of x minus 3, this represents del of x minus of minus 3. That means the impulse function appears at x equals to minus 3 with a magnitude of 0.2. This is 0.2, and similarly 0.125 at x equals to minus 2, another impulse 0.25, like this. So this represents the corresponding magnitude, and del of x, that means x equals to 0, 0.1, like this. So distribution is a staircase step form function, and density, since it is derivative of distribution function, it consists of impulse functions.